In order to understand the early universe, we have to look at the part of physics that deals with things that are very small. Because remember that the universe started in a small, hot, dense state that we call the Big Bang. Now, in today's universe that is relatively cold and boring, we have 4 different forces of nature that determine all of the interactions we have between matter and energy. And those are gravity. You know what gravity is, right? Gravity is what makes it hard to get out of bed in the morning. We have electromagnetism. This is the laws of electricity and magnetism. And then we have 2 forces that we normally don't think about because we don't experience them on an everyday level because they only work at the level of the atomic and the nuclear. And these are what are called nuclear forces. We have the weak nuclear force, which governs radioactive decay, and the strong nuclear force. And the strong nuclear force is what holds the nucleus of an atom together. And the strong nuclear force has to be strong for a very important reason. Remember, opposites attract, likes repel. Remember how hard it was for us to do fusion? Remember that those protons were like, nope, don't want to get near you because we both have the same electric charge? In order to do that fusion, we have to overcome that repulsion of those 2 positive protons, right? So we need a strong nuclear force. So in today's universe, we have 4 very different forces. But the universe was a very different place billions of years ago when it was young and hot and dense. Rather than have 4 independent forces, all we had was one, sometimes people call it a super force. There was only one force that governed the early history of the universe. And in order to understand the early universe, we have to understand the details of how that unified super force over time, over the cooling of the universe, divided up into the 4 individual forces we see today. And part of the problem in understanding that is that these 4 forces look very, very different. If you think about it, gravity and electricity and magnetism, they don't seem to have anything in common. And again, electricity and magnetism versus radioactive decay, what do they have in common? So some really smart people over many decades have been working on this problem to figure out how to unify these forces, how they actually look more similar than different at very high temperatures. And in fact, one of the first people to try to attack this problem was none other than Albert Einstein. Albert Einstein spent about the last 25 years of his career trying to answer this question. Now, Einstein attacked the problem from the wrong angle. He tried to figure out how gravity and electromagnetism could be combined. And they are probably among the most different of all the forces. What we actually have learned in the decades since then is that the 2 most similar forces are electromagnetism and the weak nuclear force. At high energies that we can mimic in particle accelerators and so-called atom smashers like CERN in Switzerland, we can actually, at very high temperatures, see how the electromagnetic force and the weak nuclear force are actually 2 sides of the same coin. They are actually 2 manifestations of a unified force called the electroweak force. In the cold universe of today, we see 2 distinct forces. In a much hotter, earlier universe, which we can model again in these atom smashers, these 2 forces combine to form the electroweak force. Now, at higher temperatures and higher energy still, so high that we can't directly make them in atom smashers, we have to do this indirectly, we think that the strong nuclear force combines with the electroweak force to make what we call a grand unified theory, or a GUT. But that is not the whole story, because there's still gravity. And gravity is the most dissimilar of all the forces. It takes the highest energy the highest temperature to get gravity to converge with the grand unified theory. And that would give us a theory of everything, a so-called TOE, or yes, TOE. If we had a theory of everything, if we could figure out how gravity converges with these other three forces at ridiculously obscene high temperatures and pressures and energies, then we would know about the very earliest part of our universe. We would know more directly about the moment of creation, about the Big Bang. So particle physicists have been attacking it this way, trying to see how all the forces can unify. And what astronomers are interested in is working in the other direction, figuring out how, as the universe cooled, first we had one superforce, the theory of everything. Then at about 10 to the minus 43 seconds after the Big Bang, gravity says, "See you later, alligator," and becomes a separate force. And then as the universe cools a little bit more at about 10 to the minus 35 seconds after the Big Bang, the strong force is like, "I am so out of here, dudes." And the strong force becomes separate. And then when the universe becomes older still, the last two forces go, "Well, it's been real. Guess it's time to break up." The electromagnetic force becomes separate from the weak nuclear force. So, this part, figured out, already gave out the Nobel Prizes. One for the theory, one for the experimental verification. The grand unified theory, we're maybe 95% of the way there. The theory of everything, highly speculative. There are a number, and calling it a theory, that's what we want to get as a theory of everything. We are not there now. What we have is a bunch of hypotheses, a bunch of models. And one of the people who's been working on this for most of his career, of course, is Stephen Hawking. And when we get a theory of everything, sometimes people will call this quantum gravity or something like that, they'll get a Nobel Prize for sure. Maybe they'll come up with a special unified prize of everything because it's just that important.